Welcome. In a previous video, we've discussed adding, subtracting, multiplying, and even a little bit about powers in modular arithmetic. We never discussed what to do about dividing. So there is a sense of division. It's just not the regular division operation, at least how it works on real numbers. So it doesn't make sense to have a fraction in modular arithmetic. So we shouldn't be writing like 1/2 mod 7 or anything like that. Because whenever we're working in, let's say, mod 7, for example, it means that we're requesting to get a remainder after we divide by 7. So the remainder itself is defined to be an integer, not a fraction. So if you're working in mod 7, the only options are 0, 1, 2, 3, 4, 5, or 6, and nothing in between. So the question still remains, what could we do about an equation like this where we maybe want to divide by 3 in regular arithmetic? So we still want to get rid of the 3, we still want to isolate x, but we can't directly because there's no divide by 3, or there's no 1/3 in mod 7. So what you can do is define something called a multiplicative inverse. This is the notion of undoing multiplication. That's what we mean by inverse. So how do we do that? Well, you pick a number that multiplies back to 1 in whatever the mod is. So if we were going to try to find some multiplicative inverses, let's try to dream up of some ways of multiplying back to 1. So if we write 1 down on our page and we're trying to work in mod 7 and get back to the number 1, let's just write mod 7 at the end of our calculations here. What would we multiply by? The question also asks, well, what about for 2? So let's write down the same thing. We'll fill in the blank afterwards. We want to find a way to multiply 2 back to 1. We want to find a way to multiply 3 back to 1, and then finally the question asks, well, what about 6? Okay, so I'll get out my green pen for the next part. So the inverse of 1, well, that one is fairly clear. It's always 1. 2, what could we multiply 2 by to get 1 in mod 7? Well, we'll just play a guess and test game for the moment. Later on, we'll come up with a better way of doing this. So you can multiply 2 by 5 and you get 10. That wouldn't work. What about 2 times 4? That would give you 8, which does reduce to 1 in mod 7. 3 times 5 is 15, which is 1 in mod 7. There's a little bit of a trick for 6. If you're ever dealing with minus 1, which is the same as 6, you could always consider minus 1 times minus 1 to give you 1 in mod 7, or whatever mod you might be working in. So 6 times 6, without doing any calculation, will give you 1 in mod 7. If you'd like to do the calculation, you sure can. 6 times 6 is 36, and subtract 35 and you get 1. So now we can put this to use and try to actually solve an equation with it. So because I'm looking at a 3, as we were above, and I'd like to get rid of that 3, our natural instinct, if you're used to real numbers, might be to divide by 3, but we're not going to do that here. We're going to think about, okay, there's a 3 there, so we're going to look above. What was our inverse of 3? Well, it was 5. So what we want to do below is multiply both sides by 5. So all of the left-hand side and all of the right-hand side gets multiplied by 5. So on our next step, so that equation implies that we have 15 x minus 2 congruent to minus 20 in mod 7. So the magic here is that the 15 changes into 1, and you just get x minus 2 on the left side. How about we add 21 on the right-hand side to get 1, and then finally, to get our answer to isolate x all by itself or solve for x, we'll add 2 to both sides. So we get 3. Okay, now, numbers don't always have inverses in a particular mod. For example, there's no inverse of 0. There's no way to multiply 0 back to 1 in mod 7 or any other mod for that matter. A way to help us figure out when we actually have an inverse is to look at relatively prime numbers. So what is a relatively prime number? You're probably familiar with prime numbers. So if we write down some prime numbers, 2, 3, 5, 7, the key about these numbers is that there's no factor other than 1 or itself in each of these numbers. So when we put the word relatively prime, what we mean is we're taking two numbers that have no common factors between them. So let's write down some examples. Let's try to think of two numbers that are relatively prime. So if you take, let's say, 21 and 10, those numbers are relatively prime. There's no common factors between them. 21 is 3 times 7, and 10 is 2 times 5. So we write RP for short. So 21 and 10 are relatively prime. But if you took 21 and 35, these numbers are not RP. They're not relatively prime because there's a common factor of 7 between them. Okay, now the upshot here is that when we're relatively prime with the mod, then we have an inverse in that mod. So if A is relatively prime with M, the mod, then A has an inverse in that particular mod. So let's think about mod 26. Let's try to think about all of the different elements or remainders, if you like, in mod 26 that do indeed have inverses. Let's write them all down. So 1 is always a possibility. 1 always has an inverse. 1 times 1 is 1. Now if you try to take 2 and you say, well, I want to multiply 2 by something in mod 26 and get back to 1, it's not going to work out. You'll never find that. Because 2 is not relatively prime with 26. So 2 is off of our list. 3, on the other hand, is relatively prime with 26. 4 is not. 5 is relatively prime. Nothing in common with 5 and 26. 7, 9, 11, and once we hit 13, we have to skip 13 because 2 times 13 is 26. And it will be the rest of the odd numbers from there. So 15, 17, 19, 21, 23, and 25, or -1. Okay, so something else that we can do in modular arithmetic is take a look at the cancellation law. So it's often nice to just cancel things out on both sides. If you see a C on the left and on the right, it's certainly visually pleasing to cancel that out, but you can't always do that. You have to make sure that C has an inverse. Or in other words, you have to make sure that C, the number that you're canceling out, is relatively prime with the mod. Then you can go ahead and do the cancellation. So let's see if we can cancel the numbers below in the example. So can the common number in each of the congruences below be canceled? So our common number here is 2, but 2 is not relatively prime with 2. They have a common factor of 2. So in the first option, we would say no. And if we tried it, just notice that, well, we have a contradiction. 1, if that's all that's left on the left-hand side, and 4 is all that's left on the right-hand side, that would be false to say that 1 is congruent to 4 in mod 2. So let's just give that the strike through. 1 is not 4. In the next example, we would say, well, can we cancel out the 3 on both sides? Well, 3 is relatively prime to 2. No common factors there, other than 1, of course, but 1 doesn't count. I guess there's that caveat above. No common positive factor other than 1. So, yes, we can do the cancellation because we're relatively prime with the mod. And if we do the cancellation this time around, it does make sense. 1 is congruent to 7 in mod 2. And notice in both cases, we did start with a true congruence. It is true to say that 1 times 2, which is 2, is congruent to 2 times 4, which is 8. So 2 is congruent to 8 in mod 2. That is true, but we ended up doing something, and we got something that would be false to say 1 is congruent to 4. And in both cases in part B, the congruence is true, in contrast to part A. Okay, so far we've discovered what an inverse is. We've given the definition, and we've talked about when they exist. Now let's discuss how many of these inverses there are. So it turns out there's just one way to find this pair. That pair is unique. We're going to prove that right now. So one way that you can prove things like this is to assume that there's 2 ways to find this pair. So we're going to assume that A multiplied by B gives you 1 in mod M, but also we're going to assume that A multiplied by B prime gives us 1 in mod M. And we'll assume that we're picking B and B prime to be different. So let's just write, and B is not the same as B prime in mod M. So what we could do with this assumption is say, oh, okay, we have A on both sides of the congruence. And A indeed has an inverse. So A can be canceled out on both sides. So this implies that B is congruent to B prime in mod M. So our assumption is incorrect, right? That we could pick B and B prime to be different and have them both be inverses of A gives us the result that B and B prime are the same thing. So we get another lightning bolt striking us down here. Our assumption that we happen to think about here has to be wrong. So we cannot pick 2 inverse pairs. There's no way to pick 2 of them. So that means that this pair is unique. All right, so that discusses how many inverses there are. Let's discuss now how to find them. And we'll use mod 26 as an example to show us. So in mod 26, previously in this video, we discovered that these are all of the possible numbers in mod 26 that do indeed have inverses. So we're going to go ahead and find them here. And we're just going to draw a line when we pair them up. So there's a couple that are straightforward. One pairs with itself. So the pair is unique, but it could pair with itself. Like every number here has exactly one friend, but you could be friends with yourself if you want. Another one that we can get right away, let's remember 25 is the same as -1. So -1 times -1 gives us 1. So there's like a self line there. Now let's try to think about some of the other numbers. So for this course, what you can do to find inverses is just write 1 down on your page. And with 1 written down on your page, try to factor it as many times as you can. Now, 1 can't factor right away because it's just the number 1. There's no interesting ways to factor that. But you can add 26 to it to get 27. And now we can go ahead and factor it. So 27 is the same as 3 times 9. And we have immediately got one of the inverse pairs. So 3 and 9 make an inverse pair. In addition, we can also use the 3 and the 9 to get another inverse pair out of this. So minus 3 times minus 9 will also give us an inverse pair. So minus 3 is 23, and minus 9 is 17. So next, if we add 26, we would get 53. So no factors there. 53 is prime. So let's just try again. Add 26, and we get 79. Again, no factors there. Add 26 one more time, and now we get 105. 105 is a gold mine of factors for us. We've got 3 times 5 times 7. So this is great. We can pair 3 times 5 to get 15. So 15 times 7 gives us an inverse pair. We could also pair 21 and 5, because 3 times 7 is 21, multiplied by 5 gives us 1. So 21 and 5. And the last pair is 19 and 11, or at least possibly that's the last pair. Maybe we should verify that that also works. So 19 is the same as minus 7, and 11 is the same as minus 15. So again, we verified that we have our inverse pair, and we found all of them, and I'd say quite quickly. This method works really, really well for smaller numbers. This is the only method that will be required to know for finding inverses. But there is other methods out there if you're really interested in doing extra research above and beyond the course. You might be interested in the Euclidean algorithm, which is a step-by-step process to figuring out these inverses, but it takes a little bit longer. So we're going to stick to this method because it's all that we need. So one more example for our video. We're now going to put all of this to use and try to solve for x in a mod 26 congruence. So on the right-hand side, we've got 7x plus 6. How about we start by subtracting 6 to both sides? So we have y minus 6 is congruent to 7x. And as we just discovered above, the 7 and 15 make an inverse pair. So we're going to take what we have and multiply 15 on both sides. And if we do that, the magic is that the 15 and 7 disappear for us because they are inverse pairs. So we finally get our result that we're looking for. X is congruent to 15 multiplied by y minus 6 in mod 26. All right, thanks so much for listening, and we'll see you on the next video.